In clinical research, prediction is often a matter of life and death. We need to predict if a patient will experience an adverse event, like a secondary heart attack, based on their specific health data. Researchers frequently turn to linear regression for these tasks. It is highly effective at predicting continuous variables, such as blood pressure or cholesterol levels, where results can fall anywhere along a numerical spectrum. However, linear regression fails when the outcome is binary. If the question is simply yes, the event occurred, or no, it didn't, a straight line cannot accurately map the data. Plotting binary data on a 0 to 1 y-axis reveals the mechanical problem. A straight line through these points produces predictions that defy physical logic. At the extremes, the line extends below 0 into negative values and pushes above 1. Predicting a negative chance of an event, or a probability exceeding 100%, is mathematically impossible. Respecting the boundaries of binary data requires a model built on a different statistical architecture. Binary logistic regression is designed to solve this bounding problem. It is the specific methodology for predicting the probability of a categorical outcome. Its core function isn't to predict a numerical value on a line, but rather the likelihood that a binary event will occur. To stay within the 0 to 1 range, the model uses a sigmoidal curve. This S-shape ensures that all possible predictions remain contained within the logical limits of probability. Because predictor values often overlap in the middle of the curve, the model calculates thresholds. A value yielding exactly a 50% probability serves as a tipping point for classifying an outcome as yes or no. This curve is made possible by the logic transformation. This is the natural log of the odds that a specific category, such as a yes outcome, will occur. By mathematically transforming the relationship between variables, the model creates a predictive framework that respects the constraints of categorical data. We can observe this in action using a heart attack dataset. We'll use stress levels as a continuous covariate and exercise prescriptions as a categorical factor to predict the likelihood of a second cardiac event. Before interpreting specific variables, we must prove the model's structural integrity. This involves demonstrating that our proposed model, H1, is statistically superior to a null model, H0, which assumes no relationship exists. This model summary provides measures of fit. We compare AIC and BIC scores. The significant decrease from H0 to H1 proves our predictive model is statistically significant. We also look at McFadden's R-squared to quantify the strength of a logistic fit. Our result of 0.383 indicates a good model fit, as scores between 0.2 and 0.4 are considered reliable benchmarks for logistic models. Confirming these metrics ensures that the individual variables we analyze next are supported by a stable mathematical foundation. With the overall model validated, we can isolate each predictor to determine its specific impact on the probability of a heart attack. The Wald test determines predictor significance. Both stress levels and exercise prescription show p-values below 0.05, confirming their influence. The most important metric is the odds ratio, describing how outcome likelihood changes for every unit of change in the predictor. As a general rule, an odds ratio greater than 1 suggests a positive relationship, an increase in risk. An odds ratio less than 1 suggests a negative relationship, or a decrease in risk. We see this with our continuous predictor, stress level. Its odds ratio is greater than 1, meaning higher stress levels are significantly related to an increased probability of a second heart attack. Conversely, our categorical predictor, exercise prescription, has an odds ratio of 0.13. This value, being less than 1, indicates that an exercise intervention significantly reduces risk. The model predicts that for patients undergoing this exercise intervention, the probability of a second heart attack is reduced to 13%. These ratios provide researchers with a precise way to quantify how specific risk factors or clinical interventions alter a patient's health trajectory. To verify that these theoretical probabilities translate to real-world accuracy, we test the model's ability to sort patients correctly. This is the confusion matrix. It serves as a comparison between the model's predicted outcomes and the actual outcomes observed in the patients. From this matrix, we derive sensitivity, the percentage of true positives correctly predicted, and specificity, which is the percentage of true negatives the model correctly identified. In this case, the model correctly predicted 15 true negative cases and 15 true positive cases, with only 10 errors. This results in 75% sensitivity and 75% specificity, meaning the model was accurate for 3 out of 4 patients. High classification accuracy validates the model's practical utility, transforming a mathematical curve into a reliable tool for clinical decision-making. The final stage of research is the synthesis of these tables and plots into a standardized report of findings. This report presents a formal summary. It connects the overall chi-square significance and the classification accuracy to the specific effects of the individual predictors. The data shows that while increasing stress drives risk, an exercise intervention provides a measurable and significant reduction in that risk. Binary logistic regression remains the essential tool for transforming binary data into validated predictive insights that can directly impact patient outcomes.